Hello, everyone. My name is Masbali. I'll be presenting Understanding Loss Functions Driving Model Success. So, in this recitation, I'll be explaining different losses and showing a dummy demonstration for each loss. So, what is a loss? It's a metric that measures the performance of a model. How? By quantifying the error between the predicted output of a model and the actual target. How does it improve the model? So actually, it tells us how much the model's predictions differ from the actual answers and helps us improve the model during training. How? By updating the model's weights. And why do we need them? Because we need the loss to evaluate the model's performance and to guide the learning process to improve the predictions. What are the type of losses? So the first type are the basic losses, and the second type is the zero-shot losses. So the first type, the basic ones, are widely used in foundational deep learning tasks, such as regression tasks and classification tasks. But the zero shot, like they are designed for tasks where the model must generalize to unseen classes, such as like applications like face recognition, speaker verification, and image retrieval. So the distance-based losses for regression. So in regression problems, we want our network's predictions to be as close to the target value as possible. So we want to minimize the distance between the prediction and the target. And the standard measure for the distance between 2 points is what is the squared Euclidean distance between the 2 points. So the average Euclidean distance between points in your batch of training data is what is the mean squared error. So the mean squared error, like let's let's think about an example, which is like predicting house prices. So like imagine you want to build a real estate model that predicts the price of houses based on different features like the size, location, and number of rooms. So your objective is to minimize the MSE during the training. So as you can see from this formula, the N is the number of data points, Y hat I is the predicted value, and the YI is the ground truth. So here, first of all, this is a template like for calling the loss. So where do we usually call the loss in a network? So we usually call it after the forward pass. So here the mean squared error, the MSE, is a built-in function by PyTorch. So here you just initialize, you say nn.mse loss, and then here you can call the predictions and the ground truth to compute the loss. The other type of losses is the classification losses. So in classification problem, the network must output the probability for the class of the training data, like network output, like PYI for each of the classes I, typically computed using what? A softmax function. And ideal output, PYI must be high, ideally 1 for the target class, and the others must be low for the remaining classes. Here we're talking like about multi-classification. So if we have different classes, this is captured by the cross entropy loss. So the Y target is either 1 for the target class or 0 for non-target classes. So the formula is actually minus log Y hat, the target class. So note that this 0, when the network outputs a perfect 1 for the target class and greater than 0 otherwise. So the cross entropy. So if we want to build a classifier that classify the images of like cat, dog, and bird. So the objective is to minimize the loss, ensuring that the predictions are closer to the actual values. So this is the formula. The n is the number of data points. The yic is target probability for class C, and the yi hat C is the predictive probability for the class C. So here, the cross entropy, the CE, is also provided, is also a built-in function by PyTorch. We just like do the following initialization and n dot cross entropy loss. Here is like examples of 3 labels, cat, dog, and bird. And here are different, here are the predictions. And now we can call, after the initialization, we can just call the loss here and compute the loss. So the second thing is the binary cross entropy, which is actually um, uh, a special case of the cross entropy. So in some problems, the network only identifies one class, a single class. Is this the picture of a leaf infected by fungus? So in this case, the network only outputs py for the target class. So it must be 1 for the positive training instances, like a picture of a real leaf with a fungus. Must be 0 for negative training instances, like a picture of a healthy leaf. Here, although there is only one output, there are implicitly 2 outputs. So probability of class like py which means positive, equals the py, and probability of not the class py negative is equals to 1 minus py. So the binary cross entropy is just the standard cross entropy for single class classifiers, where the CE is computed over both outputs py pos and py neg. So for an example for binary cross entropy is a spam email detection. A model that predicts whether an email is a spam or not spam. So the objective is to minimize the loss, encouraging the model to output probabilities close to the true label. So n is the number of data points, the yi is the target probability, and the y hat I is the predicted probability. Let's see the implementation. We have also there's in PyTorch a built-in function. So you just call the nn.bce loss, and then after the initialization, you call the BCE loss and compute the loss for the predictions and the two labels. So for example, 1 is the spam and 0 is the non-spam. So here we provided 3 examples, and the predicted probabilities are the model's confidence. Now, the zero-shot loss. So in the classification losses seen so far, we have tried to train a network to predict specific classes in the training data. So the objective was to maximize classification accuracy of the specific classes seen. So for example, like previously we've been talking like that we were training like a classifier for dog, bird, but for example, we didn't train it on a mouse. So we can't expect to have a mouse in the testing set and like expect that our model should perform well on unseen classes. So the idea of zero-shot problems that our intention is not to teach the network about specific classes, but rather we derive representations where instances of a class cluster together and far away from instances of other classes. So the specific classes we provide during training are now just examples of classes. The network must learn the generic concept of clustering instances from a class together from these example classes. So the zero shot actually losses promote such learning. So what are the differences between the conventional classification loss and the zero shot? So in the conventional classification problems, the network merely learns to model the classification boundary between classes in the feature space. So as long as the classes are perfectly separated, it would be super happy. So, but in the zero shot, we try to minimize the distance between the data points of the same classes while maximizing the distance between data points of different classes. So the cross entropy loss is actually a zero shot loss. So the network learns to extract features that are separable from each other by linear boundaries. In doing this, it learns to generate features where features from the same cluster together, but only provided there are a sufficiently large number of examples classes. So we have already seen this in the CE loss. Center loss. So in the center loss, we explicitly try to shrink the classes by moving the feature vector for each data instance towards the center of its class. So the loss itself is what is the total squared distance of all data points from the center of their respective classes. And also the centers are learned. They're learned. This loss is also used along with the cross entropy loss. So, an example for the center loss is the face recognition systems. Center loss is used in, as we said earlier, it is used in conjunction with the other losses such as CE to enhance the face recognition systems. So the model learns embeddings for face images, ensuring that all embeddings belonging to the same person are grouped closer to their center in the embedding space. So our objective is to minimize the distance between the feature vectors of sample from the same class and their class center. So here from the following formula, the M is the total number of samples in the batch. The xi is the feature vector for ith sample. CYI is center for class YI. And now we will show the implementation. So actually we don't have a built-in function provided by PyTorch. So the class is really simple for the center loss. So here actually we get the class centers for the input labels, and then we compute the square distance between features and the centers. Then these distances are clamped to ensure that they stay in a reasonable range, and the mean distance is computed to get the final loss. Here we initialize it, and then here we compute the loss functions for the embeddings, vectors, and their corresponding labels. Angular losses. So the angular losses, the losses distribute the feature vectors on the surface of a sphere by normalizing their length. Subsequently, they work by just what by minimizing the angle between each data point and the center for its class. This allows us also to introduce a margin, which is like an additional penalty for what? For being away from the center. So the angular softmax. Example for angular softmax is like also a face recognition system. So think of a face recognition system that checks people's identities by comparing their faces to photos in the database. And the system needs to make sure that the face representations, we need to make sure that face representations for different people are very different from each other's, while face representations for the same person are very similar. So, for example, the objective is we need to maximize the cosine similarity for the true class while enforcing a margin between classes in an angular space. This is the formula. S is a scaling factor to stabilize the gradients. And this is the cosine similarity with an angular margin M. And the theta is the angle between the embedding and the correct class center. For the angular softmax, we don't have a built-in implementation. So as we can see here, first of all, we normalized the embeddings and their corresponding weights. Then we computed the cosine similarity between the embeddings and their weights. Then we subtract the angular margin from the cosine similarity for the true class. And then we scaled it by a factor S. Then we computed the loss using the cross entropy. So here's both we initialized and call the function at the same time in one line. Second type of angular losses is the additive angular margin softmax. So this one, it helps make class more distinct in a classification problem. It does this by what? Adding angular margin between classes in the decision boundary. So it introduces an angular margin to make it harder for the model to classify the samples. So by adding the margin, the decision boundary becomes stricter. So same class samples are pulled close together, and different class samples are pushed farther apart. This improves the model's ability to separate classes, especially in challenging tasks. So the angular softmax can only impose an unfixed angular margin, whereas the additive margin, angular margin softmax incorporates a fixed hard angular margin. So example for the additive margin softmax, so speaker verification system. So if a system that needs to determine if two speakers belong to the same person, the embeddings of different speakers should be well separated, while the embeddings of the same speaker should remain compact. So as you can see, by the way, here, the additive margin is different from the additive angular margin. The angular margin, as you saw there, it's angular, it's an angle. But this is like just a simple margin. So this change, it should be reflected in the formula. So for example, additive margin, we just say minus m. But the angular margin, we should put the minus m inside the cosine. So the S is the scaling factor to stabilize gradients, and the C is the number of classes. The theta is the cosine similarity for the true class. So our objective is to also maximize what the cosine similarity for the true class while enforcing an additive margin to separate classes in the embedding space. This is the implementation. Again, here we apply normalization for the embeddings and their corresponding weights. Here we computed the cosine similarity. We subtracted the angular margin from the cosine similarity. And then this modified cosine similarity is scaled by the factor scale. Then we computed the loss using the cross entropy. We initialize it and called it at the same time, the same line. So contrastive losses, the losses we have seen so far have all focused on the relationship of data instances to their classes. As a result, the loss for each data instance can be individually calculated. So contrastive losses are computed by comparing data points to each other. They are built on the principle that a data point must be always closer to another data point from its own class than it is to a data point from any other class. Example, triplet loss, which is the most common contrastive loss. A use case is a face recognition system to determine if two faces belong to the same person. Example, the anchor is the stored image. The positive is a current image of your face, and the negative is a face image of someone else. So the objective is to minimize the distance between anchor and positive embeddings while ensuring they are farther from the negative embedding by a margin alpha. So fxa is the anchor, xp is positive, and the xn is the negative sample, and the alpha is the margin for the implementation here. Oh, by the way, in PyTorch, they provide an implementation, a built-in function for the triplet loss, but it's also very easy to create your own function for this. You just compute the distances for the positive and the negative samples, and then you compute the triplet loss by applying the ReLU to ensure that this loss is non-negative. Here are the references and for further reading. And thank you for listening.